Hey, what's up, guys? This is Chung here. So today, let's take a look at this problem, number 726, number of atoms. Okay, so you're given like a chemical formula as a string format. Return the count of each atom. Okay, so there are like a bunch of rules for a formula, right? Which means that each atomic element, each atom, basically each atom element always starts with an uppercase character and then zero or more lower lowercase letters representing the name. Okay. Well, actually here, yeah, zero or more lowercase letters representing the name here. Okay. And then one or more digits representing that element count may follow if the count is greater than one. Okay. So which means that if the count is one, so it means that there's no digits follow that. Okay. So for example, this is water, right? H2O is valid, but and H2O2 is also valid, but H1O2 does not, it's not possible. So, right, so if there's only one atom, so it means that there's no one followed by that. And also the two formulas connected together will produce another formula, of course. So this one is also a formula, right? And there's also like a parenthesis thing here inside here, right? As a count optionally added. It's also a formula. Okay, so you can also add parentheses. So which means that, this one is also like a formula, which means that, ending with a parenthesis, there could be one, right? I mean, it's optionally added, which means that, the H2O2 is a valid formula, and this H2O2 with a parenthesis is also a valid formula. So we have to be careful about this one. So what does this mean? What does this one means? It means that once we see a right parenthesis, so there could be a number uh, uh, after that, or there could be nothing. Okay, which mean in this case, this is not. It's also a valid one. So we shouldn't always assume there's a like a digit after this right parenthesis. That's not correct. Okay, and And also this is pretty straightforward, right? I mean, anything, let's say if after this right parenthesis, there's also like a 3 here. So it means that all, all the atoms, right? All the atoms inside this parenthesis will be multiplied by 3. So which means that we have a total, so we have a 2H, uh, 2 helium and 2 oxygen right here, right? So, and then multiplied by 3 here, in total we have a total of 6H and 6 oxygen, right? He, 6 helium and 6 oxygen here. And in the end, it just asks you to return the count of all elements as a string, and the first name in sorted order. This is just like an order, right? Followed by its count. If the count is more than one, followed by its count, which means if the count is one, we don't add one. Just similar like how this formula is given here. Okay. For example, this one, right? So H2O, the output is H2O, and for this Mg, I don't know the pronunciation for that. MgOH2, so we have in total we have one Mg, right? And then we have a 2HO, a 2O and 2H. Since we need to sort it alphabetically, right? So that's why in the end we have H2 MgO, Mg1, and then O2. So And this is another example with the parentheses, right? Like I said, we have a two two sulfur, I think this is sulfur, right? And 6 oxygen, and then in total we have a ON, and then we do a divide, we multiply by 2, so that's how we get this final out, output. Okay. Here's also like basically we have a 32 BE here, right? So that's how we get this 32 here. Cool. I mean, so this would actually this problem, is very similar as the calculator, right? I mean, if you guys have seen those calculator problem, which you have like a equation like 1 plus 2 times 3 plus 4, and then a times 5, right? So if you guys have seen those problems, this one is very similar. Basically, we have to either use like either recursion or the stack, basically, to handle this parenthesis. So what does it mean? It means that every time when we see a parenthesis, okay, basically when we see a left parenthesis, and then we know, okay, we need to start a new thread, or basically in terms of the recursion, it means that we need to start a new recursive call. Okay, and when we see like the end, right? The ending parentheses, we know, okay, so this recursion call is finished. Okay, I mean we can either use the recursion or the stack. I mean with the recursion, basically the way it works is that every time when we see like a left parenthesis, we need to find its corresponding right parenthesis, right? And then we pass the whatever the string in the middle to that recursion call, recursive function, right? And then we keep doing it until we reach the end, okay? And so to find the left the corresponding right parentheses, we just loop through everything, right? Right? We loop through everything that's in of the string here, and we basically we keep a counter of the left parentheses, and we know we find the correct right parentheses whenever the counter is equal to 0. So which means that at this moment the counter is 1. So now we have another counter. We have another left parenthesis. Now the counter is 2. So we have a right parenthesis. Now the counter will be decreased by 1, and here there is 0. So whenever the parenthesis counter is equal to 0, we know, okay, we have find that, and then we can just do a substring of that. Okay. I mean, but I think the recursive call is it definitely works. But the issue for that, is I think because the performance is a little bit slow. The reason being is that because we have to count everything here, and then we will be reprocessing those strings one more time. But anyway, it will definitely work. But today, I think I'll be using the stack. Basically, for the stack, the idea is the same, right? Basically, every time when we have like, okay, sorry, let me give you another example here. So let's say we're using this one as an example here. Okay, so what does this one mean? It means that, at the beginning, we have k and 4, right? So we have a stack. Oh, and by the way, so the value in the stack is a dictionary because we need to store both the atom name and the count of the atom. That's why the stack will have a dictionary. Okay, so this is how the stack thing works. Basically, the first one we have k and 4. Okay, I'll be talking about how can we process this, get the atom name and the count later on, but that's like a kind of trivial, right? So at the first level, we have we have a dictionary, right? There's dictionary, and k we have k and the value is 4. So that's the first the dictionary, right? And then every time when we see like a left parenthesis, we add another dictionaries on top of the stack. Okay. So now we have a new dictionary, right? So now we have O and N. Those are the two elements, right? So what does it mean? It means that we have O 1, right? And then N1, right? Because those are the two elements on top of it. And then we have another parentheses, and then we will be adding another dictionary. So now this time we have one S and three O, right? So which means that we have another dictionary here. we have like 1s, and then we have like 3o. So o is 3. Okay, right? Ah, this, I think my drawing is terrible here. Actually, let me try. Oops. Okay. Ah. Hmm. Because I was trying to draw a wider stack here. Okay. So this should be enough. Okay. Cool. So basically, every time when we see the left parenthesis, we add one more dictionary on top of the stack. Now we see the first right parenthesis. So which means every time when we see the right parenthesis, we pop the dictionary on the top of the stack. And then after that, right, since we are seeing then after that we need to find the multiplier, the multiplier after this right parenthesis, right? In this case, it is 2. But remember, like I said, so there could be no parentheses. There could be no multipliers after the right parentheses. So it could be 2 here, but it could be also none here, right? So in that case, I mean, of course, the multiplier will be default as 1. So in this case, it's 2. So after we find like uh, the parentheses, right parentheses, we pop these things out, right? So we pop these things, pop, we pop, and then we get everything inside of this stack, and then we multiply it by 2. So now what do we have? We have s equals to 2, and then o is 6, right? So we have that. But so what are we going to do with this result here? We'll add this one back to the top of the dictionary, right? So now we'll add this one to here. That's how we keep track of the current result of the dictionary, the current dictionary's result. So now this thing will become to what? So we have like how many O here, right? We have so now the oxygen becomes to 7, right? Still we have 1 N, and then we have 2s, right? And this is gone forever. So now the dictionary is on the top is like this, okay? And then now we have another like right parenthesis. We do the same thing. We pop these things. We pop. We multiply everything inside here, and then we add it back to here until in the end, all it's left. We have a big dictionary with the atom and the count inside the dictionary. Basically, after we have traversed the entire string, all it's left is a big dictionary, right? And we can simply loop through that dictionary, and then, of course, we sort that the key by the key, and then we just concatenate the final answer here. Cool. I think that's the basic idea, right? I mean, so by using a stack, we can like mimic like the recursive call. So, all right. So about implementation, I mean, so stay with me, guys. So the implementation, since this problem has many edge cases, so the implementation is a little bit long, but yeah, it shouldn't take that long time. Okay. So first, we could do an n here, right? And then we start as a stack. So we know that, at the beginning we need a dictionary, right? Because we will be counting counting for each of the element, and we do a counter because we can these things can handle the non-exist key case, right? So it will be default at 0. Okay, and we have I equal to 0, right? And then because we will be looping through the n here. So why we use I less smaller than n, not the for loop. This is because, uh, because when we have this like right parenthesis, right, we don't know how many digits after that. It could be two, it could be one, it could be two, or it could be 100, but probably not. There won't be existing that element, but that's basically the idea, because we will be skipping the i's by more than one, right? So that's why we do a while here, so that we can increase the I later on. So now we have a current character, right? So like I said, we'll be doing different things based on the current character. The first thing is, like I said, if this current character is a left parenthesis, it's pretty straightforward. All we need to do is we just append a new stack, sorry, a new dictionary on top of the stack, okay? And then we just increase the I by one, right? So that's the first thing. And second thing, right? Second thing is like this. Second is the right parenthesis. So like I said, whenever we see a right parenthesis, so the first thing first, we're gonna pop the current counter, right, out of the stack. Now, to what? Find the multiplier after this, right? So we find the multiplier after that. So how do we find that? We're looking for the digits after this parenthesis. Whenever we see a non-digits character, we know, okay, we should stop there. Okay, basically that's what we do. Since we have already processed this current parenthesis, and we need to do a I plus one first. That can help us. So basically we can keep using this I here, right? And we need a start, right? Start is the I, right? And then the way we're finding the numbers, we just simply do a while loop here, right? So the way we're doing it, first we need to check if the I is smaller than n, and formula I is digit. Formula I is digit. And then we do a I plus one. So we have to check the I here, right? Otherwise, if we don't do if we don't check the I smaller than n here, this formula I might be out of the boundaries, right? Because we're always doing an I plus one. So in the case the I is equal to the n, right? And then we should stop here. We shouldn't do this because it couldn't find it, right? So basically we keep going until we have seen a non-digits character here, and then we know, okay, so whatever between the start and this I will be our number. But remember, the base case, edge case is that there could be nothing here, right? So there could be nothing here, so which means that the if we simply get the formula, right? The formula between the start and the end, right? So there, we could have end up getting an empty string. Okay, so we have to take care of that case. So it's pretty straightforward, right? So we simply check, right? Multiplier. So we only return this thing. Oh, we only need to return these things. We convert it to integer, right? If the formula start I is not empty, right? Then we convert it into integer. Else one. Remember, so keep in mind that we have one here, not zero. Okay. If we're getting a zero, so there will be nothing to be added, right? So now we have find the numbers, and then we can just add uh, these things, multiply by this multiplier and back to the top of the stack, as if we're returning to the previously recursive call, right? So that's basically we have Adam, right, in the current counter, right? And what is a count? So we have a count. Count is the current counter uh, Adam, right? So actually we can do anyway. So this will also work. So we have Adam when we have a Adam, the count for this Adam from this dictionary, right? And then we simply do what? We have a stack -1. That's how we get the first, the top, the dictionary, right? And the key is the atom, and the value is what? The value is the atom. The key is the atom. The value is the count plus the multiplier, right? So that's how we do it. Cool. So then here we have a update the counter, right? The top counter in the stack, right? So that's how we handle these things here. And since we're always increasing this I, even during looking for the digits here. So after this while loop here, the I should be in the correct position, right? Waiting for the next while loop to be processed. And else. So we have processed I, sorry, the parenthesis case. Now it's the regular case, right? The regular case without the parentheses, like H2O or HE2O. So here also still pretty straightforward, right? So we just need to find the atom and the count. So the first thing is to find the atom, right? So we have like so the atom at the beginning is the C, right? Because the one atom always starts from as starting as an uppercase number and followed by one or more, zero or more like lowercase letters, you know. Well, actually, you know what? I think as far as I remember, so all the elements atom there are at most two characters, right? So which means there could be only one uppercase and only one lowercase. I mean, there won't be a HEE. I don't think this element ever exists. But for the case of the for the case of for the case of this problem, you know, let's still try to implement it at the safer way, right? So we're assuming okay there will be more than one lowercase after this uppercase. So first we implement it. We increase the I by 1. So basically similar like how we find the digits here, right? So we have a while loop here. So sorry, we also need a start. Okay, start equals to I, right? And then we need to find the what? The first element, the first character that is not equal to the lowercase, right? So same thing, I is smaller than, and the formula I is a lowercase, right? So it's a lowercase. Then we increase it by 1. So now uh, we have atom, right? Plus what? Plus the formula of the start, right? And then end. So here we don't care if it's empty or not because we are having a string here, right? So that's how we get the atom here, right? And then the same thing, find number, right? Find the number. Yeah, find the numbers. We can simply copy and paste here. Copy and paste this number. That's exactly the same logic here, right? Start from I, right? And then we do here. Yeah, I'll just copy and paste here. And then I plus 1 here is not a multiplier. I'll call it like count. I'll just call it count here. Okay. Same thing, right? If it's nothing there, we assume it's 1. Okay. So, and yeah, and since we are like, there's no for loop in this case because we're processing these numbers, this like atom one by one. So we can simply do a stack dot -1 dot atom. So we have atom and we do a plus count. We can simply do a plus count in this case, right? That's that. Cool. So That's how we process this like a non-parenthesis case. So we find the pair each pair of the atom and the count, and then we update the current dictionary, and then we go back to this while loop to process the next pair. Okay. So after we have processed all the strings here, now we have a dictionary, right, where we can construct our final answer here. So, and of course, I mean, we can use like a simple version of the loop here, but I'll just write this logic explicitly here so that it's easier for everyone to understand. So, I mean, the final output is pretty straightforward, right? Basically, first we sort by we sort a counter, right? And then so the answer is like this. So we concatenate the answer first, right? And but keep in mind here, we could have like a dictionary. In the dictionary, we could have like an atom with the count equals to 1, and for that one, we don't want to concatenate the numbers. So which means that we only concatenate if the counter of this atom is greater than 1, right? So and then we do a we convert it to a counter, right? Dot atom, right? And then we simply return the answer. Yeah, I think that should I think that's basically it is. Okay, let me try to run the code here. Collect collection is oh sorry, I think there's a typo here. Collections, not collection. How about later on? Is there like collections here? Yeah, another collections. Run the code. Another typo here. Line 38, formula. Formula. Okay, cool. So this one accepted. Submit. All right. So it's also accepted. Pretty pretty cool. All right. So and how about the time and space complexity, right? So we have like O of n loop here, and then mm, then we have like let me see, and then we have like this for loop here, right? Basically, the worst case scenario is that each of the time here we'll have a like every time when we have a right parenthesis, we'll be looping through all the previously element here one more time. So I think it's like it should be a O of n square. That's the time complexity, right? And the space complexity is of course, is a counter. Is the space of the stack here, right? So the space complexity is O of the hmm, is O of n. Yes, because even though we could have multiple counters, but the total numbers inside the inside the stack is also still bounded with the number of the length of the string here. So the space complexity is O of n. Cool. Yeah, I think yeah, that's it. I mean, just to recap, right? So, I mean, every time when you guys see this kind of like formula problem or the calculator problem, and with this parentheses, so the first things come to your mind is that you have to use some sort of recursive logic, right? And to implement the recursions, there are two ways. First is to use the recursive function, right, to call the function itself. And the second one is just to use the stack. And for this problem, stack is better because actually stack is always better than than the recursion, right? And the way we're using a stack here is every time we see a left parenthesis, we add a stack because that the stack is being used to hold the current recursive call. Okay. And every time when we see like right parentheses, we know, okay, so basically we're simulating, right, the recursions. And every time we see like left parentheses, we know, okay, so the new recursive call starts. And we use like this a new item in this stack to track that. And then when we see like a right parentheses, we know that, okay, so this is done. Actually, you know what? So I believe if you in the real computer science like pro programming, when they design it, they use a stack. Yeah, behind the scenes, uh, I believe they use some sort of stack to track the recursive call. Actually, we're using the stack to simulate that, to mimic that, right? And we have start of a recursion call, and then we add an item to the stack to track the current recursive call. And when we see at the ending of a recursive call, we pop the current recursive call's result out of the stack, and then we do some calculations, right? And then in this case, it's just to multiply it, and then we return it. We return it to the previously recursive call by uh, by adding, basically by accumulating the result to the previously dictionary. Okay, and we keep doing it until, of course, and this is like the regular non-recursive case, right? And we keep doing it until we have traversed all the string here. So other than that, it's just like some corner cases handling, like the empty multiplier and the uppercase and the lowercase stuff, right? Cool. That's it for this problem. I'll stop here. Thank you so much for you guys to watch this video, guys, and stay tuned. See you guys soon. Bye bye.